Air quality is hard to judge with our senses. Many existing monitors rely on numbers and technical data, when most users just want a quick glance. That was the problem we wanted to tackle with PineSense. Our idea was to translate key air quality signals like PM, VOC, and CO2 into a more ambient and intuitive interaction. Instead of reading data, the user reads the object. We designed PineSense for indoor spaces like a desk, bedroom, or living area. The aim was to make invisible environmental information easier to notice through form, light, and movement. In the early stage, we explored both product and biological inspiration. We went to Smith's toy store to look at mechanisms, movement, and how objects can feel expressive. We were inspired by the leaf sheep because its soft, organic form gave us an early direction around environmental responses. Later, after finding pine cones in Glen Falls, the concept became much clearer. Pine cones gave us a stronger biomimetic direction. They already suggest opening and closing in response to the environment. That made them a better fit for an interactive air quality object. So this was a key shift in the project. We moved from a softer, cuter idea into a stronger natural metaphor with cleaner mechanical potential. From there, we explored a wide range of ideas through sketching and ideation. We looked at elephant trunk forms, leaf sheaf concepts, more standard pinecone forms, and exaggerated pinecone monster variations. This stage helped us test different silhouettes, personalities, and emotional tones. It also helped us define the logic of the interaction early on. We started asking what the object should do in good, poor, and warning air conditions. A key lesson here was the originality was not just about making the object more expressive. It was about making it more coherent, more readable, and more suitable for indoor use. The strongest part of the project was the prototyping process. This is where PineSense really improved. We started with paper prototypes to test silhouette, proportion, and recognizability. They helped us quickly see what felt pinecone-like and what did not. We then moved into a cardboard monster prototype. This version helped us explore scale, presence, and personality. It gave the object a stronger visual identity early on and helped us test how expressive it could become. After that, we developed the 3D printed mechanism. At this stage, we had already been researching different opening and closing systems. We explored several movement ideas and bending approaches, but many were too fragile, too unclear at the scale, or too difficult to resolve cleanly. In the end, we chose a screw-like mechanism. This gave us a clearer and more controlled way to translate rotation into opening and closing. Once that was decided, 3D printing in the PLA became the anchor for the rest of the design. A digital vernier caliper became our best friend. It helped us measure accurately and refine the parts around real dimension instead of guessing. That mattered especially in the screw-like mechanism. Fit and tolerance had a direct impact on whether the system would work properly. We quickly learned that the first thread dimensions were not suitable for the printer, so we had to refine the tolerances. We also learned that support placement mattered because cleaning the thread entrance was difficult after printing. On top of that, we had repeated bed adhesion problems which taught us how important setup, heat, and print preparations were. Once the mechanism was working better, we returned to the cardboard to fix the scaling and test how the mechanism works in this overall form. This stage helped us connect the internal systems back to outer shape. It also showed us that the final concept needed to feel more mature, more coherent, and better suited for indoor environments. So we removed the eyes and other overly expressive features. We focused instead on the leaf qualities, the core opening and closing mechanic, and a more resolved product language. From there, we developed the base and outer structure, where we explored different bend shapes for the base and different leaf shapes for the top structure. In the end, we chose a hexagonal base and pentagon for the leaf. That combination worked best visually and structurally. The hexagonal base also gave us better placement for the electronics. At the same time, the cardboard stages revealed weakness in the struts. That meant we had to refine multiple vectors and structural profiles to make the form more robust. This was an important turning point because the project moved from visual experimentation into structural problem solving. Finally, we chose 3mm plywood for the laser cutter outer parts. This gave the project a more natural and biomimetic aesthetic and helped the final design feel more mature. As the design became more resolved, the process moved into manufacturer level modeling. We created both ready-to-print and ready-to-cut outputs. A big part of that was the software workflow. We used Affinity Designer for vector, laser cutting outlines, FreeCAD for more precise part modeling and dimensions, and Ultimaker Cura to prepare the PLA for parts printing. The exploded assembly was used in Blender. This was important because it clearly showed the structure of the final system. It showed the layer base and NeoPixel ring, the stepper motor, the inner mechanism core, the outer leaf ring, and the upper pinecone structure. At that point, PineSense has moved from concept into a believable fabricated object with clear part hierarchy and assembly logic. A major part of the final prototype was making the air quality states clearly visible. Those states decisions started in ideation and were later tested through Arduino Uno and NeoPixel ring and a stepper motor. For the good air state, the mechanism is more open. It uses a soft green-blue glow and a slow spin. For the poor air state, the form becomes slightly more closed. It uses an amber glow, soft blinking, and a moderate to slow spin in sync with the light. For the warning state, the mechanism reaches its tightest condition. It uses fast red blinking and quicker, more urgent movement. This helped us test whether the interaction was actually clear, and the key question was not just whether it worked technically, but whether the object remained legible and easy to understand at a glance. The final outcome, PineSense combines 3D printed PLA components, laser-cut wooden leaves and struts, and a laser-cut hexagonal base designed to hold the stepper motor and NeoPixel ring. The final design is stronger because every stage of the process contributed something specific. Paper helped with the silhouette, cardboard helped with scale and character, the 3D printed mechanism helped define the interaction, returning to cardboard helped fix the scaling, the final fabrication then stage resolved the structures, material, and assembly. What makes PineSense successful is not just the final form, it is the way the project improves through iteration. We tested many ideas. We learned that what was too expressive, too weak, or too complex, and then we refined the project into a more mature and believable product. Overall, PineSense translates PM, VOC, and CO2 into a more ambient, biomimetic, and intuitive experience of air quality. Instead of asking us users to interpret technical data, it offers a quicker and more natural way of noticing changing environmental conditions through form, light, and movement. PineSense shows how air quality data can be moved beyond numbers and become a more legible, everyday interaction using biomimicry, iterative prototyping, digital modeling, and fabrication-led design to create a more intuitive indoor air quality device.